Good day, everyone. This is the second recording I had for the week where I'm not able to do online sessions. Last time we discussed the instruction set being incorporated into the IAS, and we did a translation of the fourth factorial program with loop from the analytical engine and the IAS. At the same time, we also pointed out that there are certain incompatibilities between the jump instructions of the analytical engine and the IAS, which will force us to restructure our program from top down, from bottom up to top down loops. Okay. And this time, we will introduce a new computer with a slightly different architecture from a different generation. Okay. Remember that the ENIAC, the ABC computer, all computers during the Second World War until 1956, that's from 1940 to 1956, are considered first generation computers. It was in 1956 that IAS and EDVAC became very popular. These were the computers being developed by two competing groups, no? One from Princeton University, which is headed by John von Neumann, and the other from Pennsylvania State University, headed by Eckert and Moakley. Eckert and Moakley produced the EDVAC, and John von Neumann produced the IAS, which became known as the Stored Program Concept Computer. Also by that time, from 1956 to 1953, IBM started producing computers. In fact, a few months after the release of EDVAC and IAS, IBM also released their own stored program concept computer called the IBM 701. Okay, we will look at the instruction set of the IBM 701, but we will not study the programming about it anymore. However, a very significant event during the second generation of computers, that is from during 1960, is the birth of a new company, okay, developing smaller version of computers. Because during those times, no, IBM was developing or producing large mainframe computers. Okay, the 701 is a mainframe computer. So that company was called DEC, Digital Equipments Corporation. And they produced their small computer. It's called the mini computer in 1960. It's called the DEC PDP-1. So this second generation of computers, no, DEC, it's good to look at the architecture of DEC PDP-1 because we can show the evolution from the complicated addressing that is in the IAS and EDVAC and IBM 701 to the simpler linear addressing that is in the smaller DEC PDP computer. So, okay, here it is, no? The DEC PDP series started in the 1960s. This is in our regular site. Officially, no, in the 1960s, DEC produced its first mini computer, okay, worth $120,000. No? It's the first computer with one's complement, okay, and then followed by they were able to produce 50 of those during the 1960s. Now, the period during which DEC was very active in producing computers spans two generations, no? From the second generation to the third generation, because 1964 is already the third generation. Okay, so they called their computer a mini computer in the sense that it's much smaller than the IBM 701. Its counterpart at that time was direct counterpart was IBM. We look at IBM 701 later. Now, before we start discussing the instruction set, let's look at the design of the DEC PDP-1. I think we can have it here. Is it the programming manual already? Program data processor, okay? Here's an actual picture of the DEC PDP one in bottom up. No? So the central processor contains 18 binary digits, which means that the word is 18 bits. Now, the good thing about this is, unlike the IAS where a data word is 40 bits and instruction word is 20 bits, that uses straight 18 bits both for instructions and data, which means that this is one of the first computers that will not have to address a left and a right. Okay, which means that addressing by then, since then became linear, which means we don't have to distinguish between the left instruction and the right instruction, which is common in the IAS, EDVAC, and IBM 701. Okay? Now, the memory is 4096 words or 4 kilowords of 18 bits each. Okay, and sometimes no additional memory capacity may be added to the PDP-1 machine, like in our modern computers nowadays. Okay. Okay, it's composed of blocks, no? Like nowadays, no, we have components. They are then called blocks, no? So it has standard variety of input and output devices. Consists of paper tape reader with a read speed of 300 lines, no? Or about 118-bit words, okay? Which is the same word size that it uses. No? Okay. So here's the structure. No? If you look at the structure, it's very much like the IAS. No? It has a main memory. It also has a memory address register, a program counter, which are registered present in the IAS. Likewise, we also have the popular accumulator. Okay. So like the IAS, it has an accumulator which is 18 bits. It has an input output unit, and it can be attached to an input output register connected to an external equipment. Okay, so the control unit no has an instruction register and also has a memory buffer register. Just like in the IAS, no, when the instruction is fetched, it's fetched from memory buffer and split into two, where the instruction register contains the opcode and the memory address register will contain the operand. So if you look at this, no, this is like the IAS, very identical to the IAS, except that it uses 18-bit words, both for instructions and data. Okay, so in case of an instruction, the PDP-1 can have 5 bits for its instruction. So 5 bits can correspond to a number of instructions. Now, it also is the first computer to have indirect memory addressing, which means that during a load and a store, it can have two modes, a direct mode and an indirect mode. Now, an indirect mode is like accessing an array, where the parameter used in memory is not the value itself, but it's a value pointing to another address in memory, which contains the actual value. Okay, you will discuss this more in C# or in C++, no? Direct and indirect addressing. For the moment, no, the indirect addressing gave it a possibility to manipulate arrays. Okay. Now let's look at the buttons. This is how to operate them. The PDP-1. It will have a start, stop, continue, examine. The contents of the register of the memory indicated in the address will be displayed in the accumulator. Deposit will transfer the accumulator to memory. Read in, you will read tape reader, okay, and possibly transferred to the accumulator. Now, what's more interesting, however, is the instruction set, because if you look at the instruction set, it's very similar to the IAS, except that the jumps do not have a left and a right. So you will have an add, which can run in 10 microseconds. When you say add y, okay, you're adding the value of the accumulator from an address y in memory directly. No? So this is the same add and in the IAS. Sub y will also, in the IAS you say add m of y. In the PDP one, you just say add y. Okay, do you follow? And in the IAS, you say sub m of y. Now, in the PDP one, you say sub y. Okay, which means subtract a value from the accumulator taken from the address y. Okay. You also have a div and a mul, no? There are different divs and muls, no? Different types, but we are interested only on the div and the mul. There are logical operators, inclusive and exclusive word. Now the load, do you follow? Now in the IAS you say load m of 1 or load m of y. In the PDP one you say lac y, LACY, which means load the accumulator with the value from the address y. Okay. Now store is called dep or deposit accumulator, DAC y, which means transfer the value of the accumulator to address y in memory. Okay. There are different combinations of dep, no, but the most popular is DAC. Okay. Jump. Okay. This is the same exact equivalent of the jump, unconditional jump. In the IAS you say jump MOY, and in the PDP one you say jump JMPY. Jump and save accumulator is one of the legacies of the PDP one, which means you can do a call and then return back to where you jump off. Now, if you ask, what are the conditional jumps? Unfortunately, no, the PDP one only has single line skips. It cannot jump very far. No, can only skip one line at a time. You see, skip if accumulator and y differ. SAD y, which means that if the address y is different from the accumulator, you will skip one line, only one line. No? SAS y, skip if the accumulator and y are the same. Okay, and then there's a special skip. It's called ZA, skip on zero accumulator. There's a skip which is just a standard skip, and there's a skip called skip on zero accumulator. Okay, and there's also skip on plus accumulator, skip on minus accumulator. Fortunately, no, the skip zero accumulator can be an equivalent of CB. It's like a jump minus. Okay, although the DEC PDP one also has its own jump plus because it has a skip on plus accumulator, which means you can do both top down and bottom up looping in the PDP one. Skip on zero overflow, when during a division, no, there's no overflow after the accumulator. Okay, and many other skips. Okay, so I'm giving you an ungraded exercise to compute the average and sum of the first n numbers in the PDP one. It's not graded, however, it will be part of our first formative test. Okay. What I'm going to do now is to translate the fourth factorial program with loop from the analytical engine to the IAS and to the DEC PDP1. Our purpose here is to show the evolution of the different computers. No? Remember that the IAS is the first generation computer, no? And the PDP1 is a second generation computer. Okay. They are both the second generation computers. Okay. Before them, of course, is the analytical engine. If you look at our regular site, I have there a worksheet which I would like you to download. This is the fourth factorial conversion, okay, from the IAS, rather the analytical engine, to the IAS to the DEC PDP1. Okay. I'm going to download it and then erase its contents to show you how I created the program myself. Okay. The factorial program with loop conversion for PDP1, for the PDP1. Okay. This is the worksheet. Let's download this. Okay. Hindi na download. Oh, it's downloading. Okay. This one, huh? This should be the worksheet. Okay. So what I have here are three versions of the program. No? Okay. The same factorial program, which we translated from the analytical engine to the IAS. Fortunately, we'll only translate bottom up. No? Although we can do top down because there's a jump plus in the DEC PDP1. Okay. We'll use the same. No? We'll use the same. However, for the moment, no, I will erase all contents, no, of the PDP1 conversion of the bottom-up program for the fourth factorial with loop. Okay, so on the leftmost side, we have the analytical engine, and on the middle we have the IAS bottom up, which we have converted using a trick called jump plus, no? Jump plus, which will just skip one line. Okay, so I presume that you already know, you have already traced this, that this works. No? Our task now is to convert line per line according to the syntax provided by the DEC PDP1. Okay, so let's transpose this. No? So in the IAS, you have jump for 0 to 9. In here, you have JMP 4. Okay, that's how it's done. Okay, let's look at the instruction set again. JMPY, it's correct. Okay, to JMP4. Okay, and then this will be 4, 1, 1. So this will have 4, sorry, 4, 1, 1. Okay, same thing. Now this will be the head of our loop. So we'll translate load M2. What is load M2? Okay, let's look for that. Load LAC. They follow? So LAC. So we have LAC. That's how it is. Okay, I hope you follow, no? So when we say LAC2, the accumulator will not now have the content of M of 2, which is 1. Okay. And then we will translate mul M1. Okay. Mul is the same mul, but you just say mul 1. Okay. So mul of M1 now is 4. 4 times 1, the accumulator becomes 4. It also has the same accumulator. Okay. And then we say store M2. The equivalent of this is DAC2. Okay. Strange, no? Very strange. Why do you have to change the name? So that they will be unique. but the function is exactly the same. Okay, store and DAC, deposit accumulator. So the accumulator now will become will be transferred to M of 2. This becomes 4. Okay. Now let's translate load M1. Load M1 is LAC1. Okay. Load accumulator from M1. Okay. So our M1 is 4. So this becomes 4. Okay. You can download this worksheet, right? With all the traces. No. This time I'm just trying to reconstruct it to show the flow of the program. And then we sub M of 3. Okay. So sub M of 3 is sub 3. Okay. Sub 3. Is that sub of this? I think it's sub. Sub. Yeah, that's sub. Okay. Sub 3. So we will subtract 1, obviously, so this becomes 3 because 4 minus 1 is 3. And we say store M1. Okay. So the equivalent again of store is DAC1. Okay. So M1 will now have 3, which is our next multiplier. Okay. And then we will translate load M3. Load M3 is lock 3. Okay. Lock 3. That's according to the manual. No? So load accumulator from 3. So this will be the accumulator will become 1. Sub M1. So we'll say DAC1. Okay. DAC1. So 1 minus 3, this becomes negative 2. Okay. Now the question is, we don't have a jump. We have a jump plus the equivalent. However, we can also have the direct equivalent, which is ZSA. No? ZSA. Skip on 0 accumulator. Okay. SZA. I'm sorry. SZA. Skip on 0 accumulator, which means that if the accumulator is 0, it will skip to line 14. Okay. So the accumulator is not 0. So we will go back to the top of the loop, which will have jump 4. JMP4. This is the exact equivalent. Okay. JMP4. Okay. And in 14, we will have, of course, LAC2. And then we have MUL1. And we'll have JMP16, which is our halt. Okay. So now, going back, since this is a 0 accumulate, this is not a 0, a negative 2 is not a 0, we will go back to 4, which means we'll have to copy this. This is now our second pass. Okay. It's now our second pass. Okay. So our previous values are what are the previous values? We have here as negative 2. The accumulator is negative 2. MO1 is 3. And our partial product, which is 4. And our decrement, 4, I'm sorry. Our decrement, which is 1. Okay, let's do the second pass. LAC2. So now the accumulator becomes 4. Okay. And then mul M1. M1 is 3, so 4 times 3, the accumulator becomes 12. And deposit 2, which means the accumulator will be deposited to M2, which is our next partial product, which is currently 12. Okay. This is the same trace we had both for the analytical engine and for the IAS. Then we proceed. LAC1. Okay. Load accumulator 1. The accumulator is 3. Sub 3. Okay. 3 minus 1, this is 2. Okay. Because 3 is 1. And we say DAC1, which deposits our next multiplier of 2 to memory 1. The same trace, no? If you have traced the analytical engine, the IAS, there's no problem tracing here. We just translating line per line. Then we proceed to check our loop. Lock 3, which means our accumulator is now 1. DAC 1, 1 which is 2. So 1 minus 2 is -1. Okay. And then SZA, skip on 0 accumulator, but the accumulator is not 0. Okay. So it will not skip, it will go to line 13, and in line 13 we will go back to line 4. This will now be our third pass. Okay. This will be now be our third pass. Okay. Oh, I'm sorry, let's copy that again. So I hope you didn't find this strange. No, we're just translating command per command. Nothing strange. And then we just monitor the previous values. The previous value here is -1. The M1 is how much? 2. And then M2 is what? 12. And M3 is 1. This is now our third pass. So you say lock 2. So load the accumulator with M2, which is 12. Okay. Mul 1. So M1 is 2, so this becomes 24. Okay. And then we say DAC 2. So now we deposit this 24. 24 to 2 as 24. And then we load accumulator 1. So we are going to compute for the next multiplier. Sub 3. So this becomes 1. And we say DAC 1. So this now is our next multiplier, which is 1. Okay. And then we say lock 3. So again, we prepare for the loop. And then DAC 1. 1 minus 1. This becomes 0. We follow? Now, since it's a 0, what will happen to the SZA? Skip on 0 accumulator. Since it's a 0 now, we will proceed here. Okay. Where we do a lock 2. Lock 2 means our partial product of 24. Okay. And our last multiplier is 1. Multiply it by 1, we have 24. Okay. Okay. We don't need to store it anymore here because it's already at 24. If you want, you can do that. And then we just go to a jump. 16, which is a halt. Okay. So you can download this worksheet, study the programming. We will not do the top down anymore. Okay. Although you can do that yourself if you like. There's more than enough to demonstrate the evolution. You see how computers evolved from the analytical engine to the first generation ENIAC, EDVAC, ENIAC and ABC to the second generation of the IAS and the PDP-1 and the IBM 701. So what is your exercise? This should not be as hard as the IAS anymore, no, because you don't have to jump to a 4L or jump to a 4R, no. You just jump to a given address. Your exercise will be to do the same. Okay, but this time this is ungraded. No? Write a program to compute the average of the first 3 numbers. Only one, okay? The average of the first 3 numbers with loop. Okay? This should be exer 3 na ba? Or exer 4. You just name it correspondingly. This is due until the end of the month. This is ungraded, but this will be part of the exam, which we'll have on the August 26th. Okay, so you have to solve this because this will be part of the exam. Now, let's look at the IBM 701. Oh, the main difference is the IBM 701 is a larger computer, no, which has 24 word lengths. 24 word lengths. 24-bit words. Okay. The memory consists of 2 kilowords, each with 13 bits length. Okay, do you follow? Operate on individual 18-bit quantities. Which means that the numbers are 18 bits. But the instructions, did it say? Okay. The instructions are 18 bits, but the words are 36 bits. Do you follow? So it's a slight variation from the IAS, because the IAS is 20-bit instructions with 40-bit words, 40-bit operations, and the IBM 701 has 18-bit operation and 36-bit operations both, no? Because it can handle 18-bit words and 36-bit words. Okay. Here is a sample program, okay? Transfer is the jump. No? Transfer on overflow, which means that during division, if there's an overflow, no? Transfer on plus, or it's just a jump plus, no? Okay. Transfer on zero, it's like a jump if zero or SZA. Okay. Sub is subtract. Reset and subtract, which means you subtract and reset the accumulator back to zero. Okay. Add is add. Okay. Radd is reset and add. Okay. Store is the same store. Okay. Store address, which means store the accumulator to a given address. Now, extract is like load. How memory address? No, it will extract to address to another address. Okay. Store will transfer the MQ. Store MQ will transfer the MQ register because there's an MQ register now. But the ordinary store will store the accumulator to the given address. Div will divide. Round will round. Multiply is MPY. Okay. So for sure, if you are asked to do the factorial program here, you'll be able to translate it line per line, because the IBM 6701 is IBM's version of the IAS. Okay. It was released a few months after IAS and NVAC. Okay. And during the 1960s, no, although the PDP-1 came late, because the PDP-1 was introduced in 1960. Okay, it's almost the third generation already. So I'll post a set of questions, no, that you would like to ask, a link, no, so that if you would like to ask questions regarding the PDP-1 programming, you can post it there. Earlier, Tony Labrador posted a question and saved it in Loom. However, I cannot seem to hear the audio, so I requested him to send me a text question. Now, at the same time, I'd like to inform you that your practice test is already up, no, until August 25. This is the same coverage. No? I have emailed you the coverage of the of our first formative test. The practice test is up there, and you can do the practice test. It's almost the same as the test. Now, for the moment, I encourage everyone to read the generation of computers from the third to the fourth. No? We already have discussed the second, no? The third and the fourth generation, and then the history of Apple computers. The history of the computer monitor is very important. The history of the IBM PC, no? Very important. Also, the history of Microsoft Windows and the history of the internet. Okay, So please post the questions. I'm going to put I'm going to add. Let me add that now. Forum questions. Forum. Forum. Questions on PDP. Okay. Okay. I'm just going to transfer it to right after PDP1. Okay. It's there already for you to post your questions. So I'll be making about 1 or 2 more videos regarding history of computing. So please keep in touch. I'll upload this to our website. Please watch the recording.